Atmospheric Pressure Chemical Ionization, APCI. APCI is an ionization technique using gas phase ion molecule reaction at atmospheric pressure. The nebulizer consists of 3 concentric tubes. The eluent is pumped through the innermost tube in nebulizer gas and makeup gas through the outer tubes. The combination of the heat and gas flow dissolvates the nebulized droplets, producing dry vapor of solvent and analyte molecules. The solvent molecules are then ionized by a corona discharge. The results of these reactions produce water cluster ions, He plus H2O and a protonated solvent, such as CH3O2+, H2O and HeO with N plus M less than equals 4. These ions enter in gas phase ion molecule reactions with an analyte molecules, leading to solvated, protonated analyte molecules. Subsequent declustering, removal of solvent molecules from the protonated molecule, takes place when the ions are transferred from the atmospheric pressure ion source towards the high vacuum of the mass analyzer. Proton transfer reactions are major process, while other reactions such as adduct formation and charge exchange in positive ion mode or anion attachment and electron capture reactions in negative ion mode are also possible. Atmospheric pressure ionization, APCI. Atmospheric pressure ionization, APCI. Ion evaporation. Chemical ionization, APCI analogous to C for compounds with MW about 1500 Da. Produce monocharged ions. Electrospray ionization, ESI. Method used to produce gaseous ionized molecules from a liquid solution by creating a fine spray of droplets in the presence of a strong electric field. Electrospray ionization/mass spectrometry, ESI/MS, which was first described in 1984, commercial available in 1988, has now become one of the most important techniques for analyzing biomolecules, such as polypeptides, proteins having MW of 100,000 Da or more, in the eyes of Finn. Although ESI is now in daily use all over the world, its component processes and mechanisms, especially the dispersion of the sample liquid into charged droplets, and the formation of gas phase ions from those droplets are poorly understood. Professor John B. Finn. Several kilovolts. Few microliter per minute. 320 to 350 K, 800 or 100 milliliters per second. Bar and Thomson model. Charge density increases. Rayleigh limit, Coulomb repulsion equals surface tension. Coulomb explosion, forms daughter droplets. Evaporation of daughter droplets. Special features of ESI process. Little fragmentation of large and thermally unstable molecules. Multiple charge. Linear relationship between average charge and molecular weight. Easily coupled to HPLC. 21. Applications, assumptions. Determination of MW and charges for each peak, Smith et al. Anal. Kim, 1990, 62, 882 to 899. Assumptions. The adjacent peaks of a series differ by only one charge. For proteins, the charging is due to proton attachment to the molecular ion. This has been an excellent, but not crucial, assumption of nearly all proteins studied to date where alkali attachment contributions are small. Ionization of only the intact molecule. Z1. Z2. Given these assumptions, equation 1 describes the relationship between a multiply charged ion at MZ_P1 with charge Z1 and molecular weight m. MZ. P1. P2. P1 Z1 equals M plus mod 1 equals M plus 1.0079 Z1, 1. Assume that the charge-carrying species, Ma, is a proton. The molecular weight of a second multiply protonated ion at MZ_P2, where P2 greater than P1, that is J peaks away from P1, for example J equals 1 for 2 adjacent peaks, is given by P2Z1J equals M plus 1.0079Z1J, 2. Equations 1 and 2 can be solved for the charge of P1. Z1 equals JP21.0079, P2 P1, 3. The molecular weight is obtained by taking Z1 as the nearest integer value. Electrospray. What happens when voltage is applied? http://www.newobjective.com/electrospray/spray_anem.html. These images are framed captures of a pico tip spraying 5% acetic acid and 30% NEO at 200 ml per minute by direct infusion from a syringe pump. Each frame differs by an applied voltage of approximately 100 volts. The tip to inlet distance was Ca. 5 mm. 900 V, no spray 1000 V, Taylor cone/droplet oscillation, more drops than spray 1100 V, cone/droplet oscillation. Approx 50% spray 1200 V, cone/droplet oscillation, on the verge of a stable Taylor cone 1300 V, stable cone jet 1400 V, cone jet on the verge of jumping, slight instability 1550 V, multiple cone jets. Ionization mechanisms. Coulomb fission assumes that the increased charge density, due to solvent evaporation, causes large droplets to divide into smaller droplets, eventually leading to single ions. Ion evaporation assumes the increased charge density that results from solvent evaporation causes Coulombic repulsion to overcome the liquids. Surface tension, resulting in a release of ions from droplet surfaces. How many amino acids? ~1 charge per 1000 Da. 4 easy steps to ESI. Production of charged droplets from electrolyte dissolved in solvent. Shrinkage of charged droplets by solvent evaporation and droplet disintegration. Mechanism of gas phase ion production. Secondary processes by which gas phase ions are modified in the atmospheric and ion sampling regions. Kabarl Chang, Anal. Kim. 1993, 65, 972A 986A. Electrospray ionization process. Plus. Dash A. Emitter. Ground. Dissolvation. Coulombic. Explosion. Dissolvated. Ions. Glass. Capillary. -2 to -5 kV. End plate. -2 to -3 kV. 36 kV. 0.3 to 2 cm. 106 volts/m. Liquid flow. Production of charged droplets. Voltage difference between the emitter and counter electrode establishes an electric field, E106 Vm. For positive ion mode. Emitter grounded, counter electrode biased VA, 2 to 6 kV. Emitter biased plus VA, 2 to 6 kV, counter electrode usually plus VA if UV. Liquid flowing through capillary is conductive. Electric field at dip, E. 2 volts. E equals lane R V counter electrode capillary R D HV Taylor cone. Accumulated charge at surface leads to destabilization of surface because ions at surface are drawn toward counter electrode yet can't escape surface. Leads to formation of the Taylor cone. Q equals 49.3. Capillary Taylor cone, surface tension and droplet production. The cone instability is profoundly influenced by the surface tension, G, of the fluid. The onset voltage, VON, required to initiate charge droplet emission is related to surface tension by 4D. VON equals 2 by 105 GR 0.5. Lane R. Thus, onset voltage is higher for liquids of higher surface tension, 4 kV for water, 2.2 kV for methanol. Relative ranking: IPRO less than MeO less than ACCN less than DMSO less than H2O. The higher the voltage, the increased probability of electrical discharge, especially in negative ion mode. Corona discharge also increases with decreasing pressure, so this is why ESI is done at atmospheric pressure. Parameters influencing droplet size. The radius, R, of an electrospray droplet depends upon fluid density, R, flow rate, VF, and surface tension, G. Thus, higher VF result in larger initial droplet sizes. Larger droplet sizes lead to lower ionization efficiency because the droplets are not so close in size to the Rayleigh limit. RVF 2 grams 1/3, droplet shrinkage. Now that the charged droplets have been released from the capillary, they are accelerated toward the counter electrode. Shrinkage of the droplets results as a combination of two factors: solvent evaporation, droplet disintegration by Coulombic explosions, Rayleigh limit. When charge Q becomes sufficient to overcome the surface tension which holds the droplet together, Coulombic explosions begin. Q2 equals 64 P2/3. Where Rho is the permittivity of vacuum. ESI advantage is soft ionization technique controllable fragmentation. Readily coupled to liquid separations. Produces intact non-covalent complexes. Multiple charging of analyte. Capable of ionizing large molecules, to MVA, ion sources, old ESI design. ESI Z-spray source. ESI, protein analysis. Peptide sequencing by nano-electrospray mass spectrometry. N+17. Electrospray spectrum of horse myoglobin, MW 16951.5. Multiply charged ion distribution from +12 to +24 shown at low resolution. The +17 charge state at a resolution of about 15,000 showing the resolved isotope peaks. N+17. Concentration and sensitivity. Limitation of ion current. Electrochemical reactions occur in last few micrometer. Ions extracted per unit of time to the ms is limited by the current produced by the oxidation or reduction process at the probe tip. ESI is a constant current electrochemical cell. Too many ions from salts will decrease the abundance of sample ion. If too diluted or a very low flow, ion flow from capillary will be insufficient. Oxidation or reduction of solvent or sample will occur, producing radical ions. Analyte concentration and ion intensity. Analyte concentration and ion intensity. Atmospheric pressure photonization. Atmospheric pressure photonization. Desorption electrospray ionization. Other ionization techniques. Ionization method. Typical analytes. Sample introduction. Mass. Range. Method highlights. Electron impact, A. Relatively small. Volatile. GC or liquid. Or solid probe. To 1000. Daltons. Hard method. Provides structural info. Chemical ionization, C. Soft method. Molecular ion peak, N+H+. Electrospray, ESI. Peptides/proteins. Non-volatile. Liquid. Chromatography. To 200,000. Soft method. Ions often multiply charged. Matrix-assisted laser. Desorption, MALDI. Sample mixed in. Solid matrix. To 500,000. Soft method. Very high mass range. Fast atom bombardment, FAB. Carb/peptides. Viscous matrix. To 6,000. Soft method, but harder than ESI or MALDI.